Glad to hear that. All right. I intend to have fun today. Okay, number 1. Shauna. Number 2. I got an email saying that course evaluations, I know it's not over yet, but they started sending them out, are available. You know, your standard questions, and I added a few. You know, whether you strongly agree, strongly disagree, thing. If you haven't taken those before, you should see that in your official university email. I'm like the midterm one. This one's a little different, but same idea. I strongly encourage you to fill those out. I won't see these until after I submit grades. They're anonymous anyway, but I would appreciate it and learn from them, especially the written-in answers. So if you take a moment when, I guess now to the end of the semester, to fill that out, I'd be most grateful. And third, I meant to ask when I had the series and parallel circuits out, and I forgot. What's the purpose of a fuse? We discussed it, but let's see who you remember.
It's to prevent too much current going into the circuit that can handle that power.
Excellent. It's to prevent too much current flowing through something you don't want to. So if your fuse is 10 amps, it's going to blow if more than 10 amps go through it to protect your circuit. So, should you hook a fuse up in series or parallel, or does it matter? Who thinks parallel? Who thinks series? Who's not sure? Who doesn't care? Well, we're kind of split. Okay, let's say you hook it up in parallel. If the fuse blows, can current still get to your device? That's my point. It depends on where you put it. Yeah, if you put the fuse right out of the battery before it can split up, then it can work. But do you see that if you put an individual fuse on each device, though, the current's already split up by the time it gets to the device and its fuse? So if that, say my washing machine, that fuse blows, will that protect my washing machine? Yes, because that fuse is connected how with the washing machine, series or parallel? So now we got more series, or you're more confident. If a fuse needs to be in series with the thing it's trying to protect, because otherwise if it has another path to get to that device, it doesn't do any good. Does that make sense? So if you do it right out of the power supply, if things are hooked up in parallel, and the power supply sees I don't care what's out there, there's lots of devices, but if it draws too much current in the first place, yeah, it'll shut them all down. And that'll protect it. But usually the fuse is right on the device, and it's in series with the device, so that if the fuse blows, it breaks the circuit and current can't get to that device. If it's in parallel with that device, then there's another way to get to it, and that's not protecting it. That's what I wanted to make sure I said. Magnetism. More magnet stuff. So it's very similar to charges. You know, we had two types of charges. We have two types of poles. There's forces between the poles. More people are familiar with magnets than they are with the charges. And you know, north poles repel other north poles. Boing. But north and south attract. Repel. And it gets the other color. If I flip it around, doink. Anyway, you get the idea. There's a force. It follows the inverse square law. It depends on the strength of each field as well as the distance you are. And what's the cause of all magnetism? Say it louder. I can't hear you. Yeah, the motion of charges. And here you have the electrons. They're spinning and they're revolving. Yeah, the root of all evil, no, the cause of all magnetism is motion of charges. If you have an electron, does it have an electric field, a magnetic field, or both? An electron, does it have an electric field, a magnetic field, or both? Both, because it's a charge, has an electric field, but it's moving, so it has a magnetic field. Moving charge makes a magnetic field. So all the little electrons in here, the atoms, if the net alignment is in one direction, like think of all the little itty-bitty compasses in there, if the net alignment of those is in one direction, then you have a magnet. It's magnetized. If there is no net alignment, then it's not a magnet. Okay. I like a few things. There's magnetic things all around. Did you know that the ink they put in U.S. currency is magnetic? It's one of the other counterfeiting measures. So I folded up a dollar bill. I take it's a pretty strong magnet, I won't lie. It helps concentrate the ink in one corner. So it's, yeah. I think that's cool. And my other favorite is total serial. 100% of your daily needed iron allowance. It's one of the best ones. So here's a flake of total. We'll toss it in here. It's floating on the top. I'll bring the magnet near it. Let's see. Yeah, well, you'll be able to tell. And I bring it near and can drag it along wherever I want. And that's because of the iron in it. You can try this at home. I decided not to do it today, but if you take a bunch of this and then cover it with water, throw it in the blender, or just mush it up. The better you mush it up, the better. That sounded redundant, but you know what I mean. Pulverize it so it's a mush. Put it inside a Ziploc. Take one of them strong neodymium magnets, and if you just kind of slowly move the magnet on the outside of the bag, touching the bag, any iron filings that got released from the total get attracted to the magnet, and they'll come and collect, and you can drag them along, and then you come above the water line, you can pull the magnet away, and you'll actually see the iron filings that are in your cereal. Yes, this is safe, this is normal, but total has a lot, and it's more conspicuous. You can try it with any food you want, but you should. I can see it when I do it with total, just because of the iron inside of it. Kaboom! I'm going to get this out of the way for all the other wonderful things I'm trying to do. Let's magnetize something. These are already magnets. The paper clip is magnetic. It's not a magnet, but it's magnetic. So it's attracted to a magnet. But because it's in the magnetic field now, it's temporarily magnetized. The analogy is, remember how we polarized charges and the charges kind of rearranged so it kind of temporarily became charged? You can think of this as temporarily becoming magnetized because another paper clip will stick to it. This is super strong. Let's try. Yeah, whatever. And if that one gets magnetized, then that one can stick to it, and this one can stick to it, and this one can. That's not magnetic. And so they're temporarily magnetized. And if I remove it, the external magnetic field, dang, it's not what I wanted to happen. It's just too strong. Let's go with this. There we go. Okay, they stick. Then I remove the magnet. And they're still magnetized because the net alignment is still there. But you can mess that alignment up by banging them, thermal motion, and now I bet they don't stick to each other. Nope. Without that external magnetic field to keep them aligned, they don't stay aligned. If something stays aligned after you remove that magnetic field, then we call it a magnet. It's good. That's how they magnetize these. They exposed it to a really strong field, lined them up, and they stay that way. However, if I beat on this enough or its temperature increases too much, this will become unmagnetized, demagnetized. But I can remagnetize it by exposing it to a strong field again. Yeah. It does wear off, the paper clip sticking together after I move the magnet. Well, if you don't bump it, no, actually it would, through just thermal agitation. As they move around, they're moving all the time because of their temperature. And so they'd eventually not have a net alignment. I just sped it up. Hit it with a torch, it would have been a lot faster too.
So by banging it on the table, it'll mess up the alignment? That's how
Yeah. Yeah, this is a magnet, but if I bang it enough, not so hard that I break it, this will become less magnetized. And most things, as their temperature increases, become less magnetized also. Refrigerator magnets. A lot of people think, oh yeah, here's a big North Pole. No, remember poles come in pairs, the magnetic loop. Magnetic fields have to loop. They go from which pole to which pole? North to south. But then through the magnet, they come back. They're a closed loop. These actually have a bunch of strips of magnetic fields. You can think of it as like, here's a North Pole, and a South Pole, and a North Pole, and a South Pole, and so on. There's a bunch of those. You can tell if you take two of your refrigerator magnets. Let's see. If you slide them back and forth, you can't tell. They're like doing this. The north of this north is attracted to this south, let's say. And they just kind of slide. But what if we went this way? They would alternate, and they'd attract and repel, attract and repel. So I don't notice it here, but if I slide it the other way, can you hear that? It's not smooth. And it's because the alternating poles are trying to, instead of just staying aligned with an opposite pole. It's kind of fun. So that's how your refrigerator magnets work. Who remembers these? We still record information on magnetic tape. That's what's inside this thing, the tape. And what do? You expose it to a strong magnetic field, and the little microscopic compass needles inside align. Maybe in this spot they align that way, but here they align this way. And this way, and then this way, and then this way. And you can record bits of information that way. It's like it's on or it's off. It's a 1 or a 0. Same with, it's easier to see, your VCR tapes or your audio cassettes. Hard disk drives still record a lot of their information magnetically. And it's just by magnetizing the microscopic atoms inside. And they stay that way until you read it back. That's the next chapter, how we read it. Oops. Yeah, well, fix it later. Yeah, I've had to fix many a VHS tape. Okay, which pole is on the top of this one compared to the bottom of that one? Yeah, they must be the same. They could both be norths or both be souths in order for it to repel. You can have some fun. You can like squash it down and then... So remember, it takes work. If two poles don't want to come together, just like two charges that don't want to come together, it takes work to force them together. You store energy in the magnetic field. If I let go, it releases that energy. So there's energy stored in a magnetic field just like an electric field. Okay, this is kind of fun. Semi-related. I'm going to drop it. What do you expect the magnets to do in relation to the stick? Go down and hit the bottom and recoil. Say again?
The top one will fall slower.
The top one will fall slower. Why is that?
Because it's still being repelled. So, even though the field's moving away.
Yeah, it still feels a repulsion from this guy, right? Yeah, she's onto it, right? This guy, gravity's pulling him down, but this guy's pushing him up. If we can, when free fall, make it weightless, it's like he doesn't feel gravity for a moment, And this guy dominates the force.
So wouldn't the downward force on both of them be equal, meaning the only force at the top of the field would be the upper?
Yes. Which is, yes. I'm not going to repeat that one. Okay, ready? It happens fast. I find it more conspicuous watching the external ones. Watch what direction they go. I notice that the middle one seems to say put. This one goes up in relation to the stick, and this one seems to go down. Ready? So while it's in free fall, they're weightless. Gravity's still there, but it's falling with respect to this, so they're falling together. And so essentially the only thing there is the magnetic force. And they're trying to repel each other already. We just make that more conspicuous. Kind of fun. Here's another fun way to show attraction and repulsion. The things under the tape are neodymium magnets, and the balls are magnetic. They're steel. I'm going to put this here, take this one off, and I'm going to slowly roll this one in. What should it do to this magnet when it gets closer and closer? Speed up, because it's attracted by the magnetic force. Well, it's going to run into this and make a collision. What do you expect these balls to do? You remember Newton's cradle with the swinging balls where they ka-chunk, ka-chunk? I expect maybe if they get enough transfer of momentum, transfer of energy, maybe one of these will knock off and keep going. You ready? That means I did something not right. Let's try it again. If somebody would be kind enough to give me the can, I'll do it again. Thank you very much. No, it doesn't work again. You have to reset it. And I didn't have it set properly the first time. So it comes in kind of slow, and then I like showing this because you can store energy in a magnetic field. So a lot of people are like, oh, it started slow, and all of a sudden it gained energy at the end. Well, where did that energy come from? The magnetic fields. It was stored in the magnetic fields. How did the magnetic fields get it? Movement of electrons. Well, that's what makes the magnets magnetic, but no.
That's the same, the magnetic version of Coulomb's law.
Magnetic version of Coulomb's law. Yeah, the force between the poles.
Yeah. Since the distance was closed more quickly, the force that came out was larger.
Repeat that?
Since they were moving more quickly when they entered the field, they came out more quickly.
Since they were moving more quickly, they entered it. Yes, if those were charges. Yeah, these aren't magnetic, but that'd be true. If this was a moving charge and we moved it faster, you would have a stronger magnetic field. Very good observation, but these aren't magnets. And the net charge is 0. So we can't consider these moving charges. I'll give you a clue. We have to conserve energy. Do you remember how it took work to separate charges? I just did work to separate it, to pull it away from the magnetic field. And then I stored it over here on the other side, a little farther away. So now there's energy stored in that magnetic field. So when this guy comes along, it can knock him free. That energy that's being stored is then released. And that's how it gets faster. So I do work, it stores in the magnetic field, and we release it here as kinetic energy. Yeah?
So it's not stored in the ball bearings?
It's not stored in the ball bearings.
Stored in that magnetic field?
The magnetic field, yeah. This is being bound to this, so to speak. It's attracted to it.
What causes the ball, the non-magnetized ball, to eject?
What causes the non-magnetized one to eject is this one comes in, it gets attracted. It was farther away, it comes in, hits it with some energy, and that energy is transferred through mechanics, momentum and kinetic energy. And if it's enough, more than this one's being bound by, it releases him, knocks him free. And he ends up going a little slower than this guy came in, but then he speeds up to the next guy, and each time it gains a little bit. I've seen some YouTube videos where there's like 15 of these, and they're breaking light bulbs and things as the thing shoots out. It's kind of fun. In theory, the longer it gets, the faster it should get. However, it's not a linear thing. You're going to run into, it's going to kind of taper. That's fun.
Is there any machines that would just fragments?
Any machines? Not that I know of, things like that. It's more kind of just cute. Okay. Can't do this with normal new TVs anymore. But your old cathode ray TVs, they shoot an electron beam from the back, moving charges. And they go through the shadow match, this piece of iron, and then hit the phosphors on the screen, red, greens, and blues. I tweaked this one a little bit. And they have a coil of wire back here that can help deflect the moving charges. We're going to get into, if you have current flowing through a wire, what do you get? We did that at the end of last lecture. If a current's flowing in a wire, what do you get? Magnetic field, because those are moving charges. And so now we have moving charges in a coil of wire that create a magnetic field. And then we're going to send moving electrons through that magnetic field. Magnetic fields exert forces on moving charges. Moving charges make magnetic fields, so it makes sense that magnetic fields can exert forces back on moving charges. See the symmetry? And so here's what I want to show is you can deflect these moving charges with a magnetic field. That's how your screen would work, but it's more fun to bring up a permanent magnet. And you can deflect them around. And so they're getting deflected. They get deflected sideways, perpendicular to their motion. I'll discuss that in a moment. Any of you guys bought those bunch of magnets so you can play and make buckyballs and things? These are all little magnets. And if I open it up, I should have a north and a south pole. I don't know which is which, but... And if I hang that in front of the screen, yeah, I can see it influencing. But look what happens when it closes. What's going on there? This guy's magnetic field doesn't seem to be influencing the screen anymore. But if I open it, now they do. It's exactly. Remember, the magnetic field lines are a closed loop, and they go through the magnet. So if it's closed, most of the magnetic field lines are inside. It's very weak out here, and this is not enough to influence this. But when I open it, now we got field lines going outside of the magnets, and they can affect the electron beam. Why does it stay like this when I remove the magnets? Because this temporarily magnetized the iron mask that they're shooting through, and it's now a magnet. That's why you never wanted to, remember, did you tell your kids, don't put a magnet near the TV? That's why. Yeah, well now they make them out of different things and they don't work all this way, so it's not as fun, but...
So what's the significance of the different colors?
Red, green, and blue are, those three colors of light can combine to make any other color. And so they use those on a TV to make your picture. Yeah, and that's one topic we won't have time to discuss this semester. But red, green, and blue are the primary colors of light. The three together make white. Do you remember that LED that looked kind of yellowish? But it was actually a red and a green LED. Red and green together make yellow. Light. You can see behind, the beam just comes this way, and here's the coil of wire. Let's discuss how that worked a little more. move to this guy. This is just a high voltage power source. So there's a difference in voltage I'm going to put on these two ends. It's going to set up an electric field and cause an electron beam. Can you guys see that? This little thing is phosphor, and wherever the beam goes, it makes them glow, like in a fluorescent tube. But it shows you the path of the moving charges. They're going this way. So, moving charges make magnetic fields. So magnetic fields can influence moving charges. Can you bring this near? It deflects. And if I switch the field, what do you expect? I think that's awesome. The direction matters too. It doesn't speed it up or slow it down. It gives it a sideways push. It's a perpendicular deflection. It's best if the magnetic field is coming out of this magnet that way, and they're moving perpendicular to it, then they get the strongest influence. If I do it over here, it's parallel. They're moving parallel with the magnetic field. It needs to be perpendicular. I love the symmetry, though, of moving charges make magnetic fields, so magnetic fields can exert forces on moving charges. Let's do this one. I'm going to send current through these coils of wire. We did that on the overhead, and you saw the magnetic field with the compass needles, and it affected a compass needle when I sent current through a wire. This is just a whole bunch of wire that's coiled up on itself. And so, I hope you at least expect that when I send current through here, it's going to create a magnetic field. And if you coil it up, it has a neat effect of, instead of, if it's just going through a wire, the magnetic fields go around in circles around it. But if you coil it up on itself, do you see how it might be going around this way, but this way, and this way, and this way? You can kind of get it through the middle, and then you put them all together. The bottom line is, this coil of wire is going to establish a magnetic field that might look like a bar magnet. One end will be north and one will be south. And if the current goes the other direction, it'll set up a magnetic field in the other way. And this coil is wrapped around some iron right here. What's going to happen to it? It's going to get magnetized. So this is an electromagnet. I just got 4 D-cell batteries here. Close the circuit, current's flowing. Why are those warm? This worked right before class. I think I just drained them. Yeah, they're getting wussy. Okay, this is good though. I feel that these are warm. So somehow these are, even with the switch open, somehow it's drawing current from these. Because they wouldn't be warm otherwise. There's a chemical reaction going in there. They're doing work and they're heating up because of the resistance. That's not what I wanted to happen. But I can tell I need to check this circuit because something's closed when I don't want it to be. With fresh batteries, it holds this whole thing up. And then when I let go of the switch, it's no longer magnetized. Take that out, let them cool, and if I didn't use them up too much, we'll try it again at the end. But that's how an electromagnet works. Just put something you want to magnetize inside a coil of wire, send current into the wire, makes a magnetic field, magnetizes your core, and you got an electromagnet. You can pick up cars that way. Here's a magnetic field. It's going that direction between the 2 poles, and I'm going to send a lot of current through this wire. And it's going to be going perpendicular to the magnetic field. So what do you expect to happen when I close this switch? What's going to speed up?
The electrons?
It doesn't speed up the electrons. The magnetic field will exert a force on those moving charges to deflect them sideways. So I expect that if this is strong enough, we should see the wire move. You ready? I don't want to leave that one connected. It's enough of a force. That magnetic field is exerting a force on those moving charges when they're going by. Enough to raise the wire up. So that's one kind of convincer that charge really is flowing. And it doesn't have to flow fast. We know it's not, the individual charges aren't, they're just kind of drifting along. But that's enough. They have enough energy per charge, voltage, that they're influenced by this strong magnet. What if I change the direction of the magnetic field? It'll go down. I don't know if you can see it. It's not as exciting. But you can see it sag a little. That's why I like having it go up. I wonder if it'll jump this far. Ooh, yeah. Open. Good. So, do you see Newton's third law thing going on here? It's like the moving charges make a magnetic field can push on the charges. Newton's third law kind of rears its head everywhere. Superconductors. Do you remember us talking about conductors and insulators? Well, this is a superconductor. Conductors allow electricity to flow through them freely. Insulators don't. A semiconductor is somewhere in between. Doesn't conduct as well as a conductor, but it's not an insulator either. Somewhere in between. So what the heck's a superconductor? Its resistance, yeah, actually completely disappears. You remember when we put that coil of wire in liquid nitrogen and we cooled it? What happened to its resistance? It decreased, which allowed what to happen to the current? Yeah, you drop the resistance, more current flows. So a superconductor, when it gets below a certain temperature, not only does its resistance decrease, but once it drops below a certain temperature, whoosh, its resistance goes away completely. And it has zero resistance. There's just a little black disc here. I'm going to turn on the camera once it's chilled so you guys can see what it can do. Turn on the camera. I'm going to bring a little neodymium magnet near it. Helps if I plug in the light. Here we go. And this magnet is going to exert forces on the charges in there and make them move around. They're going to cause currents to flow. All right, this black thing right there is the superconductor. It's not quite below its threshold temperature yet, but it's pretty darn close. Now it is. So let's put the magnet on top of it. And it levitates. What the heck's going on? The magnet causes currents to flow in the superconductor. And because the superconductor has no resistance, none of that energy is dissipated. Charges are now flowing in the superconductor. Moving charges create magnetic fields. And that created magnetic field is repelling the magnet's magnetic field. And it makes it levitate above it. That's what a superconductor can do. We would love to make all our power lines superconductors because you wouldn't lose any energy as the current went through because there'd be no resistance. This is just a fun way to kind of show the effect. Let's see. If I rotate this a little, so yeah, that worked. I can blow on it. Make a little motor or something, you know. And that spins for quite a while because there's nothing to slow it down but air resistance. Those levitating trains, have you heard of those? If you can get something to levitate up above, then you're not rubbing. There's less friction. So they don't waste as much energy. And they're more efficient and can go faster. Oh, well, that's a good one. It's still going. This is called the Meissner Effect, if you want to study more about the Meissner Effect. Another person's name, of course. And as the superconductor warms back up, its resistance will increase, the current will dissipate, it will no longer induce a magnetic field and can't levitate the magnet. But we're not going to wait that long, because, you know, that's like watching grass grow. Did I hear you say that? Just all right. So, I'm moving into this is a perfect lead into chapter 25 with electromagnetic induction. Electromagnetic induction. You guys, this is our last chapter. You excited? And there's only really one more thing to share with you, and that's this electromagnetic induction, and then how you can put these things together to make generators and motors and create electricity and run power and whatnot. Electromagnetic induction is a changing magnetic field induces a voltage in a nearby conductor. So if you have a change in a magnetic field, you can get a voltage out. And what does the voltage do? That pushes charges around. So there's another symmetry. Moving charges create magnetic fields. Changing magnetic fields can make charges move. Not only can a magnetic field make a moving charge move, or deflect, sorry. It has to be moving though. But if you change the magnetic field, you can get the charges moving in the first place. But change is the key. Notice the charge either has to be moving to be influenced, or the magnetic field needs to be changing or moving to influence the charge. So again, electromagnetic induction is a changing magnetic field can induce a voltage in a nearby conductor. Yeah? It will. Whether you notice the effect depends on your circuit and the resistance and all that good stuff. But yeah, it's influencing it. And I'm going to show you that right now. So this is a coil of wire. It's connected up to this thing. It's called a galvanometer. Think of it as like a multimeter, an ammeter or a voltmeter. You can use it either way, but the bottom line is if current flows through it, it flows through a little coil down here that's next to a magnet. If current flows through that coil, it creates a magnetic field, correct? That magnetic field interacts with the permanent magnet's magnetic field and will cause the needle to deflect. But the only time I expect well, you can observe. Ready? Here's some magnets. Trying to get it so you can all see. When does the needle move? Yeah, when it moves. There's still a magnetic field. This still feels the magnetic field, but it's not changing, so no current flows. This coil must feel a change in magnetic field. So when I bring this magnetic field nearer to it, it's an increase in magnetic field, and the current flows one way. Now it's used to the magnetic field, it's not changing. If I remove it, it feels a decrease, and the current starts flowing another way. If I flip it around, up, vice versa. So I'm generating electricity. That's what a generator does. Do I want to keep doing this? Well, sometimes it's easier to rotate. What if I just had something mechanical make this thing spin? Well, there we go. We just generate electricity. And that's how it's pretty much done. But notice this too. I can move the magnet, or I can move the coil. As long as the coil feels a change in magnetic field. So you can move the magnet, or you can move the coil, or you can move both. Do you remember me saying, I think you asked, microscopically again, if they're, the electron, one is spinning up and the other is spinning down, then they make magnetic fields in the opposite direction? Well, what if you pair two of those electrons up? They effectively cancel each other out. Individually, they can make it deflect. But together, see how wimpy that is? But if you have a net alignment, so they're in the same direction, much stronger. So that applies here as well. There's a third way to induce a voltage in here. I'm going to use this coil. This one's connected to a DC power supply. I'm going to turn on the switch. It's going to provide a voltage and move current around through here. Now walk me through what happens next. Current's flowing in here. So what happens? It'll have a magnetic field. Because if charges are moving, this will have a magnetic field. This will essentially become like a big bar magnet. You know, like this. And there'll be north to south, or the other way, depending on which way the current's flowing. It'll be like one big bar magnet. Good. Current's flowing, there'll be a magnetic field. What else?
It'll be just like you stick in the bar magnet to the next one.
Yeah, if this guy has a magnetic field, it'll influence this, can't it? Good.
Well, I was going to say, did you say it was DC or AC?
DC. So when I turn it on, current will flow. Current makes a magnetic field. Is the magnetic field going to be changing?
No.
Why? Because it's DC. Direct current is always going to go in the same direction. And once it gets up, you know, okay, now we're going to be at whatever I set it to, 6 volts. It's not changing. What's the only thing that can cause charges over here to move? A change in magnetic field. So here we go. I turn it on. Are we getting current? Is there a magnetic field? Yeah, but it's not changing, so there's no induction of voltage over here to push the charges around. Let me turn it off. There you go. So there is a change when you turn it on and when you turn it off, but not shortly thereafter. So again, change is the key. So how could we keep this going? Not that one. Always changing. We can move the magnet, we can move the coil, or we could alternate the current on this. This is essentially a transformer, bare bones transformer. It takes your power on your primary coil, your primary circuit, and through electromagnetic induction, you can induce a voltage over here onto your secondary coil, your secondary circuit, and drive something. But do you see that it only works if there's a change in the primary? So that's why transformers will not work on with a DC circuit. You need an AC circuit to continually keep it alternating and changing. You can change the direction too. If I do it this way, what do you expect to happen? Stronger or weaker? How come? Because it's perpendicular. It's logical. Let's find out. This guy's magnet that he sets up is along this axis. This is like a north pole and a south pole. And so it's going this way. And so when the current increases, the magnetic field increases in this direction. And when you turn the current off, it decreases and it decreases. But it's always in this direction. This guy doesn't feel it then. You need to aim it into it. Let's do that like this. Here's my magnet. I'm going in and out of the coil. You can see it. What if I go this way? Not as effective. That's what was happening. So, like that. Not as effective. So if you put it like that, now this guy's field is aligned with how this one wants to be influenced. You can also put a core in here. Let's magnetize. When this current comes on, let's let it magnetize this bunch of iron. Let's see what happens. Yeah, that helps. Because not only do we have the change in this magnetic field, but it magnetizes this, and he changes temporarily and adds to the field. So transformers usually have an iron core in them. Here's a kind of a model transformer. You have 2 coils. Oh yeah, go ahead.
So if you were to take the cord that's connecting that first coil, if you take the cord that's connecting that first coil to the DC, what's it up there, and just took it out of the DC, what's it, and stuck it into the wall, that'd be an alternating current. Wouldn't that manipulate the second coil?
Absolutely. That's both influence. This DC influences the field this creates, and that field influences this guy. But only when there's a change in that field. So DC, we only see a change when I turn it on and off. Plug it into the wall that it's AC, and it's constantly changing. And so it would constantly affect this guy. And so we would see a constant current, but it would be alternating. We're going to get to that next time, it looks like. It's an actual DC or AC generator. We'll review this. But that's the essence of a transformer. You got a coil on your, say your primary that you plug into your power source. And no, they're not electrically connected. If there's a change in current flowing through here, then that creates a change in the magnetic field. And that change in magnetic field induces a voltage over here. That's electromagnetic induction. And so that voltage will cause charges to move on this side, on the secondary, and you can drive something. Notice it goes around this core. It's way more effective on that than it is just like this. This would be better than this, because see how they're lined up? This core effectively does that. It magnetizes the core and it's channeled over into here, closed loops, and so we're directing the field lines into the secondary just to make it more efficient. And we'll talk about the turn ratio of the coils later and what you can do with that. But do you have any questions at the moment? Can I end with one more demo? You'll like it. And I think we want this guy. So this is a copper tube. And I'm going to drop an aluminum slug through it. Ready? It's real exciting. Now I'm going to drop a magnet down it. Is copper magnetic? No, it's not. Otherwise it would just stuck right to it. But it is a conductor. And so here's a magnet that has a magnetic field. If I bring it near it, does the copper feel the magnetic field? Yes. Does it induce a voltage in the copper? No. Why? It's not moving. So what if I move it? By dropping it. As it moves by, the copper feels a change in magnetic field. Thus a voltage is induced in the copper to make the charges in the copper start moving around. And if those charges start moving around in the copper, what do they create? A magnetic field that interacts with that magnet to slow it down. I love this. I could do this for hours. But that's how I'll end. Thank you. The final is Wednesday, May, what is that? 2nd or 3rd? It's a Wednesday. It's on my syllabus. It's on the university's posted site.
Is it going to be in?
It'll be in here at class time.